Hey there, my name is Ryan Hedgecock. Welcome back to another video. I've got a little tidbit I want to share, but I also want to expand on it. So I think I'm going to call these tidbites. Scrumptious. I want to talk a little bit about unsafe code in C#. Most importantly, how you can stay safe when using it. When making games in the Unity engine, you almost never have to touch unsafe code. Some of you may have never even heard of it. In fact, a good number of you could go your whole life without ever needing to touch unsafe code. But if or when you do have to use unsafe code, it can be pretty scary. I mean, it must be called unsafe for a reason, right? Well, in some sense, you should be a little scared, but it should definitely not be because you don't know what could happen. I want to demystify unsafe code a little bit. I want to go over what it is and why it is called unsafe, how Unity has handled it in their own codebase in a few places, and other ways to handle it on your own if you need to. This will by no means be a comprehensive overview of unsafe code, but it'd be a great place to get started. With that said, let's get into it. So what is unsafe code? Unsafe code is code that requires you to surround it with an unsafe block that looks a little bit like this. You can see in the example we use something called a pointer. In fact, the only reason that the unsafe block exists is because of pointers. So what is a pointer? A pointer is a value that points to a spot in memory where a variable's data lives. So in the example, we have a floating point variable called value. The number exists somewhere in your computer's RAM. We then take the pointer to the variable using the AND symbol. That extracts the address that the value exists at, which is some random point in memory. The float pointer can now be thought of as containing the home address of the value. This can be pretty nice because sometimes there's quite a bit of data at that address, but instead of copying around all the data when you need it different places, you just give the address. Now everything's all fine and dandy. Our value exists somewhere in the RAM, and we have an address pointing at its location, and that pointer may be used at any time to get the data from the address. However, something dangerous is afoot. Let's say value moves homes, or, bless their soul, value gets taken to a better place by the garbage collector, and the house is destroyed. Well, the pointer still points to the same address, but who knows what could be residing there now? It may not even be a float anymore. So now, if you were to read data at that address, it would be anyone's guess what you get back. Or even worse, if you write data to that address, you could be completely corrupting the data for some unrelated object now sitting in that spot in memory. This can cause what is called undefined behavior in the programming world. It has been the bane of many programmers for a long time, and will usually end up crashing the program. So when C# came around, they decided to protect these pointers behind the unsafe wall, so that you can only use them if you know what you are doing. Let's look at how Unity uses unsafe in their codebase. With the introduction of the job system and the burst compiler, Unity has started to use a lot more unsafe code in their codebase. In a lot of cases, Unity will be creating memory outside of the scope of the garbage collector and just giving you a pointer to the location that it exists at, which contains the value. However, because it's outside the garbage collector, this isn't cleaned up automatically. We will take a look at the native array struct as an example. There is a void pointer. This represents a pointer that could be anything. But the other thing here is actually a managed object called dispose sentinel. This is a safety mechanism that Unity has added to make sure that memory gets cleaned up. A problem that can happen when we are allocating memory outside of our managed space is the fact that the garbage collector has no idea that it exists, which means that we have to be sure to clean it up manually. Unity has a slight remedy for this by using the dispose sentinel. It's a managed object that exists within the scope of the garbage collector, so that means when the garbage collector comes around to clean it up, it will call something on the object called a destructor. That looks a little bit like this. A destructor is called when the garbage collector cleans up the memory for an object. This destructor is utilized by Unity to watch over and clean up the memory related to the struct it was in case it is never disposed. It will also throw a warning that looks something like this. It will give these warnings because having a managed object in the struct along with other safety checks can affect performance, and in builds will often be disabled. So Unity encourages the developer to find and clean up these leaks themselves before release. However, Sometimes you will have to write your own native objects and use unsafe code on your own without the help of Unity's nice wrappers. This is what I did when I was improving performance in my previous video. The big thing you always have to think about is making sure you create an architecture that cannot be used incorrectly. And if you must leave around unsafe code unprotected, you should make sure to keep it heavily tested. In my last video, I chose to go the route of completely protecting my unsafe code behind an assembly definition. And in that separate assembly, I only expose native code in a way that I'm pretty sure is completely safe. This is done in a similar way to Unity's method, except instead of having a dispose sentinel inside of the struct, I opted to wrap all native objects within a managed object called native box. Native box is not an object you will find online, it is a custom object that I've created to manage native objects. It looks a little bit like this. To start off, I keep the native struct stored in a member of this class, and I have a check to make sure that the object is not disposed already. The native box constructor is kept internal, as we don't need to be creating these outside of the assembly. Just like the Unity example, we use a destructor. The destructor will call release unmanaged resources to release the native object. And in the event that the object is disposed manually, we can suppress the destructor so it doesn't try to dispose twice. Now, to be fair, this only covers the problem of leaving behind memory, and not the problem of dangling pointers to old memory positions. But the idea is the same. You want to try your best to keep pointer logic to small, discrete objects so that you don't lose track of what things can go wrong. All in all, I have covered what unsafe code is and why it is so dangerous. I've also showed a few ways that unsafe code has been handled by Unity and by me. I hope that armed with this newfound knowledge, you can be more confident in your adventures in the world of unsafe code. It can make some truly crazy things possible. So go out there, have fun, and be a little bit dangerous. I'll catch you next time.